to give jet V1 to study path length dependent energy loss using the data from star experiment. So I think, as many of us know, Sooraj, he has a long history at RHIC. He was a postdoc here for 3 years, working on heavy flavor measurements with star heavy flavor tracker. Then later he moved, he joined Kansas State University as a research scientist, but still affiliated and stationed at LBNL, continuing working on star experiment, but on the big energy scale phase 2 program. He is now the current star physics coordinator, so he has a deep, good understanding of the overall physics for star physics program, but more particular on quite a few topics, including the jet V1 measurement that he's going to tell us today. So Sooraj, if you're ready, please go ahead.
Thanks, Zhenyu, for this kind introduction. Okay, and yeah, first of all, I would also like to thank the organizers of the HIT talk committee for having me on today and for this opportunity to talk about these new measurements. So I'll be talking about the measurement of the jet V1 to study the path length dependent energy loss in heavy ion collisions at 200 GeV. So these are mostly based on the preliminary results from STAR, but I will also discuss some future prospects and outlook. In heavy ion collisions, one of the defining features we have of the QGP formation is the parton energy loss in the color charge QGP. And this is most evident in these jet suppression observables, for example, measurements of RA or yield of jet or heavy flavor hadrons in AA relative to number of binary collision scaled PP yields. But this is measuring the overall suppression of the jets passing through the QGP. But it's also important to understand what the path length dependence of the energy loss of the partons in the QGP is, like how the energy loss varies with the path length the partons traverses through the QGP. So it is also important to gain insight on the parton energy loss mechanism in the QGP, because different energy loss mechanism can have different path length dependences. And typically, we have that measurements relative to the second order event plane to study this path length dependent energy loss. For example, the measurements of V2, which is quantifying the difference in suppression in plane versus out of plane. And more recently, we also have measurements of the event shape selected events, where we try to vary the V2 or the ellipticity of the collisions and try to vary the in plane versus out of plane path length difference, and try to use that to study the path length dependence of energy loss. So one of the complications or features of this is that because V2 is a second order harmonic, the variances of all these event by event geometry fluctuations contribute strongly to it. So alternatively, we can look at the jet V1. So V1 is the first order harmonic. So this is the mean of Px over Pt, while V2 is the mean of Py square minus Px square over the sum of Py square plus Px square. So there are several advantages in looking at V1. One is that it is an alternate observable, and you can access energy loss without need for PP measurements, because it's a self-reference observable. You are looking at the path length asymmetry in a given system. And this can be advantageous in many cases where your PP baseline is limited in statistics, for example. And as I just said, it is less affected by the event by event geometry fluctuations, because for V2, it gets contribution from the variance of all these fluctuations. So it has different sensitivity compared to the V2. And as I will discuss in the next several slides, we also have some constraints to evaluate the initial path length difference that drives the V1. Another interesting aspect is that the bulk V1 is very small. It's more than an order of magnitude smaller than the V2. So this means that the evolution of the asymmetry as the system evolves or expands is much weaker compared to the second order or higher order harmonics. And this is advantageous, particularly from a modeling perspective. So let me briefly go over the origin of the jet V1, because it is somewhat different from the higher order harmonics like V2 or other harmonics. In heavy ion collisions, there is a offset in the initial density distributions of the hard scattering profile, which come from binary collisions, and bulk particle production, which comes from the participants. So if you look at a heavy ion collision along the impact parameter direction, so in this case, x direction, if you look at the forward-going participants, because there is a radial dependence of the nucleon distributions inside the nuclei, if you look at the forward-going participants, they are more dense along the positive x direction. While if you look at the backward-going participants, they are more dense along the negative x direction. So you have a x dependence in the participant distributions. And this will translate into a asymmetry or x dependence in the bulk particle distribution at finite rapidity. But the hard particle production, this comes from binary nucleon-nucleon scattering, and it does not have this asymmetry. So if you look at finite rapidity, what you have is for jets at finite rapidity, it will see different path lengths along the back parameter direction, depending on the forward or backward, depending on if you are looking at forward or backward rapidity. So if you're looking at forward rapidity, it will see more path length along the positive and back parameter direction as opposed to the other direction. And this will drive a V1. So you can clearly see this asymmetry in the bulk particle production if you look at the asymmetric collision systems, for example, D gold. This, for example, is showing the D and D eta in D gold related to that in PP. And you can see that in the gold going side, where there are more participants, you clearly have more bulk particle production. And in the mid rapidity region that we are looking at, this asymmetry, the dependence of the asymmetry on eta is largely linear. And it is driven by the participant asymmetry. So this equation I took from one of Mikolaj's papers, where he shows that you can describe this asymmetry in the bulk particle production using the asymmetry in the participant distribution and a linear dependence in the particle emission as a function of eta. So given we have a participant asymmetry along the impact parameter direction, this will translate into a initial density asymmetry along the x direction. So you can demonstrate this. You can take global simulations and look at the forward and backward going participants. So these are the transverse distributions of the participants from global simulation for mid-central collisions. And if you look at the forward and backward going participants separately, you can clearly see that they are offset along the impact parameter direction or the x direction. And then you can convert this with the model for particle emission. So I take the same model that I showed in the previous slide from Mikolaj's paper, and I use the same parameters that he has in the paper. So you can convolute with your participant distribution, and then what you get is at finite rapidity, you will see that your distribution is offset along the impact parameter direction or x direction. So this participant asymmetry translates to the bulk particle asymmetry at finite eta. So you can quantify this asymmetry. You can calculate this mean x. So that basically quantifies the tilt or the shift of the bulk particle density distribution. You can calculate the mean x and plot it as a function of eta for different centralities. And that's what is shown in this plot. So this is from the Glauber plus this model for particle production. And you can see that at finite eta, we have a finite tilt or offset in the mean x, which would then mean that you have different path length along the positive and negative impact parameter directions. So instead of using this Glauber plus model, you can directly look at a simulation. So you can take AMPT and look at the initial parton distribution. So these are partons before they enter the cascade. And these are shown in the open markers here. And you can see that from the AMPT also, you get very similar values. The eta dependence of this offset is largely linear, and it's also quite similar in magnitude to what we calculated from this Glober and particle production model. This is not surprising because HIGing uses AMPT uses HIGing as the for the initial entropy production, and HIGing very well describes the d and eta in d-gold collisions. So it is constrained by this particle production in these asymmetry collision systems. And that's why it gives very good agreement here. So we have an idea of what the extent of the initial path length asymmetry is and what its eta dependencies. In contrast, if you look at the hard particle production, you won't see this asymmetry. For example, I took this from Sandeep's paper, where he shows the profiles of the thermalized matter, which is the bulk in dotted circles here, and the binary collision profile from the shown in the solid lines. You can see that the binary collision profile is symmetric, doesn't have any asymmetry along the impact parameter direction. But the thermalized matter or the bulk distribution has this asymmetry that I just discussed. So this creates a initial hard-soft asymmetry. So this creates this tilted bulk. And at finite rapidity, if you look at jets or hard-produced particles, they will see different path length along the positive impact parameter and negative impact parameter direction. This we have seen before, in fact, for other hard probes. For example, we had looked at the D0V1. So this was published in PRL a few years ago. What is shown here is in blue markers is the D0V1 as a function of the rapidity. And you can see that the D0V1 is strongly enhanced compared to the bulk V1, which is at the sub-percentage level, shown in these black markers here. And this enhanced magnitude of this D0V1 is quite well reproduced, although not very quantitatively. But the enhanced magnitude, this order of magnitude larger V1 is reproduced by the models that take into account this tilted initial conditions and this initial hard-soft asymmetry. We also see this large V1 for other hard probes. For example, we had also the measurements of high PT charge hadron V1. So these are for charge hadrons in between 7 to 10 GeV, so quite hard for RHIC energies. And you can also see that the V1 is an order of magnitude larger than that for the bulk V1. So then the advantage or interest in looking at jets is that we get access to the parton kinematics and the parton energy loss in the QGP. So for these measurements, we are looking at the using the data collected by the STAR experiment in RHIC runs 2014 and 2016 for the gold data sets. This is 2 billion minimum bias events. We are also looking at the isobar datasets. This is ruthenium and zirconium collisions. The large statistics datasets collected in 2018. This is 3.6 billion minimum bias events. For the first order event plane reconstruction, we are using the 0-degree calorimeter, which is situated in the spectator region. The first order event plane resolution for these different datasets as a function of centrality are shown in this figure. The open markers are for the two gold datasets in run 14 and run 16. And the isobar datasets are shown in the red and blue markers. For jets, we are looking at charged particle jets with a high PT leading hadron requirement. This is to suppress the combinatorial background. We require that there is a hadron of at least 4 GeV present in the jets. We are looking at anti-KT R equal to 0.2 and 0.3 jets, and using the standard KT algorithm for background energy density calculation and subtraction. The jet PT shown are the reconstructed jet PTs. They are not unfolded, but they are corrected for the underlying event. We did check the results by changing the leading hadron PT requirement. We increased it to 5 GeV, but it didn't change the results, and the variations are within the systematic uncertainties that we have. For the systematic uncertainties, we also looked at jet area selection variation. and also impact of jet PT resolution. We didn't unfold results, but we took the jet PT resolution from detector effects and background smearing in heavy ion collisions, and smeared our jet PT in a data-driven way to evaluate the impact of the jet PT resolution on the measured V1, and this is included in systematic uncertainties. In the analysis, we did not, in the underlying event subtraction, we did not correct for the bulk V1 because, as I said, it is very small. It is at the sub-percentage level. But we include this maximum possible contribution from this as a systematic uncertainty as well. Okay, then let me move to the results. So these are the measurements of the jet V1 as a function of the jet eta for two jet PT bins with the jet reconstructed jet PT between 7 to 10 GeV on the left plot and between 10 to 12 GeV on the right plot. These are for R equal to 0.2 jets, and the constituent PT cut is greater than 0.2 GeV and has a leading hadron requirement of greater than 4 GeV. You can see that at finite eta, we have non-zero jet V1 for both these jet PT bins. And if you quantify this eta dependence using a linear fit and the slope, then you can see that the values of the slope are more than 5 sigma and more than 3.5 sigma in the two PT bins. So we have non-zero jet V1 measurement measured in heavy ion collisions. In our star acceptance, we have limited eta coverage, and also at present we have limited precision. Instead of fitting to a first order polynomial, we can also fit to a second order polynomial. Because when we looked at the path length asymmetry, we saw that it is largely linear in eta. So it'd be interesting to look at how this V1, which is a response to this path length asymmetry, what is its eta dependence? This would also tell us the path length dependence of the jet suppression. And this is what is shown in the right plot. With the current precision, both the linear dependence and quadratic dependence are compatible with the data. But with future better precision measurements and more differential measurements in eta, we would be able to make a better statement on the eta dependence of the jet V1 and potentially the path length dependence of the jet energy loss in the QGP. Compared to the measurements to other hard probes, so if you compare to D0 V1 or charge hadron V1, we see that the magnitude of the jet V1 is comparable. So within uncertainties, they are comparable. And this is again order of magnitude larger than the bulk V1, which is at sub-percentage level at 0.2%. So for now, we quantify the jet V1 using the slope. We fit a first order polynomial and quantify the jet V1 using the slope. And this is what is shown in this plot as a function of the reconstructed jet PT in the purple markers here. Also shown is the corresponding measurements for the charge hadrons in these green markers. So at low PT, we see some PT dependence for R equal to 0.2 jets and also for the charge hadrons. At higher PT, we don't have enough precisions to tell what the PT dependence is. The purple markers here are indicating the bin boundaries for the jet PT bins. We also have looked at jets with R equal to 0.3, and that's shown in the right plot. Within the current precision, we don't see a strong sensitivity to the jet radius. The measurements are consistent within uncertainties. We don't have new theory calculations to compare to at present, but we have contacted some groups, and they said they will provide hopefully in time for our paper. But in his paper, Mikolash had a calculation for the jet V1. He predicted this jet V1 much before we did the measurements of the D0 V1. That's what is shown in the right plot here. So in his paper, he has a opposite convention to what we have in STAR. His density asymmetry has a negative slope versus eta, And so his V1 has a positive slope. You can see more details in the backup. But if you look at the magnitude of the V1 in mid-central collisions, which is comparable to the centrality that we have here, you can see that the predicted magnitude is, the magnitude from his calculations for the jet V1 is quite comparable to what we measure in the data. So he predicts about 3%, and we measure about 2 to 3%. We can also calculate the jet mean px. That's a mean momentum asymmetry along the impact parameter direction, because V1 is directly related to the mean px. And this is shown in this plot as a function of jet eta on the top left two plots in two jet PT bins. And the slope quantifying this mean px as a function of jet PT on the right plot. So what we see is that there is a mean momentum asymmetry of 0.23 GeV with these statistical and systematic uncertainties for R equal to 0.2 jets in mid-central gold-gold collisions for 10 to 12 GeV jets. So this is related to the jet energy loss in the medium. But we are still trying to quantify it, how it exactly relates to the, because this is the mean momentum asymmetry along the x direction. So we are but it's also sensitive to the jet PD spectra. So we are trying to still quantify how it exactly relates to the momentum loss in the QGP. We also have looked at the isobar collisions. So these are smaller collision systems compared to gold-gold. So the overall jet suppression is different compared to what you have in gold-gold. But what matters to us is how the initial asymmetry compares between the two collision systems. And if you look at the initial asymmetry, that's a mean x between the two centralities in the two systems that we are looking at. So gold-gold is shown in the black markers here, and isobar case is shown in the red markers here. These are from AMPT looking at initial partons. You can see that the initial asymmetry is quite comparable between these two systems, because the radial distributions or its gradient doesn't change too much between these two collision systems. So even though the system size is much different, we expect to see similar V1 between these gold-gold and isobar collisions. And that's what we see in the data. So the left plot is the measurements from isobar collisions in ruthenium-ruthenium and zirconium-zirconium collisions. Again, the slope as a function of the reconstructed jet PT. And if you compare the magnitudes to that in gold-gold collisions, they are quite comparable within the uncertainties. And as we expected from the similar initial asymmetry that we see in these two collision systems. We also looked at the centrality dependence. So we don't have enough statistics as present to look at the centrality dependence with the jets, but we can do the centrality dependent measurements for charge hadrons, high PD charge hadrons. And that is shown in these red markers here. These are for charge hadrons in 5 to 10 GeV. And you can see that in mid-central and peripheral collisions, there is weak centrality dependence. And as you go to more central collisions, there is a drop in the V1. And this is expected because if you have a full overlap of the two nuclei, then there is no asymmetry along the x direction. And this is also following the initial density asymmetry that we see from AMPT, which is shown in the black markers here. It has, you have a weak centrality dependence in mid-central and peripheral collisions, and they drop as you go to central collisions. And this is exactly what we see in the data as well. Before I go to my summary, I would also like to talk a little bit about what we can do further to study the pattern-dependent energy loss using this observable. As I said in the beginning, this tilt or this asymmetry along the impact parameter direction is driven by the participant asymmetry. So you can select on the participant asymmetry, or in collisions, you can select on the forward-backward multiplicity asymmetry to engineer this tilt, to vary this tilt, and to then, you can vary the tilt or the pattern difference, and then study the pattern difference with these event shape engineered events. This is an illustration of that. This is looking at AMPT collision again. Yeah, in gold-gold collisions, in mid-central collisions. The left is looking at the multiplicity fluctuations in the forward region. So this is between 2.1 to 5.1 in eta. So this is corresponding to the EPD coverage for star. And I believe S-Phoenix also has an EPD with a similar coverage. So probably applies to that as well. So what is shown here on the x-axis is the forward-backward multiplicity fluctuation. So in each event, I look at how many particles are in the positive eta in this interval and negative eta, and then calculate the normalized difference and plot that against the against this asymmetry along the impact parameter direction at a given eta. And you can see that there is a very strong correlation, as you would expect, because this asymmetry is driven by these participant fluctuations. So these are, again, the asymmetry for initial partons. The right plot is a very similar plot, but this is now directly looking at the participant fluctuation. So instead of the multiplicity fluctuations, you're looking at, you're selecting on the, your x-axis is the forward-backward participant fluctuation. So you see very similar correlations in this case also. But when you go to multiplicity fluctuations, it's slightly weaker because, you have additional fluctuations from particle productions contributing to that. So then you can make selections on these multiplicity fluctuations and you vary your mean path length, and this is what is shown here. You can select on both directions, on positive fluctuations and negative fluctuations. And you can vary the mean path length or this tilt by by 3 times in both directions, and this will help you vary the initial path length difference and then study your response or jet V1 as a function of this path length. So one thing I want to point out here is that when you select using these final multiplicity fluctuations, it's actually very close to selecting on the participant fluctuations. As you can see in the right plot here, the red markers are selecting using the final multiplicity fluctuations, and the blue are selecting using the participant fluctuations. And you can see that in both cases, you are selecting events with very similar x. There is some small difference, and which can be completely explained by a simple particle production model, as you can see here. You can take a simple particle production model. You can look at the multiplicity distribution in the forward eta region, fit it with a globber to evaluate the particle emission from a single participant, and combine it with this eta-dependent asymmetric emission. And then you can completely model this fluctuation that you see in these MPT collisions. The red markers here are the participant asymmetry, distribution of the participant asymmetry. The blue markers are the final multiplicity asymmetry. And the pink ones are the, you take the participant asymmetry and convolute it with the model for particle production, the global emission plus the asymmetric emission as a function of it, and you can completely model this particle emission. And you can also see that on the right plot. So you can make selection on the initial participants or the final multiplicity fluctuations, or using this particle production model. And you can see that you can very well constrain this initial path length asymmetry using this final particle multiplicity distributions. Yeah, so that brings me to my summary. So I've shown that the jet V1 is an attractive tool to study the path length dependent energy loss in the QGP. And I've shown the first measurement of non-zero jet V1 in heavy ion collisions. We see an order of magnitude larger V1 compared to that of the bulk, and similar to the measurements that we see for other hard probes. We have also measurements in isobar collisions, which are consistent with that in the gold-gold collisions, as expected by the similar initial density asymmetries that we see. With the high statistics data in the upcoming years at both RHIC and LHC, the jet V1 can be a valuable tool to study the path length dependence of the jet energy loss, and also the study this path length dependence for jets of different flavors, substructure, etc. And I've also shown that you can also engineer this path length difference or this tilt by selecting on the forward-backward multiplicity fluctuations, which you can do with EPD or a forward detector. And then you can vary your initial tilt or path length difference, and you have very good control in how the initial tilt varies or the initial participant asymmetry varies with the final multiplicity selections. And then you can use that to also to study the path independence of energy loss in the QGP. So that's all I had. If you have any questions, please go ahead. Thank you for listening.
Okay, yeah, thank you, Sooraj, for the nice talk. Anybody have a question? Yeah, Wenbing.
Yeah, thanks for nice talk. Could you turn to page 25? Yeah, I just want, is it possible to extract such similar result based on the experimental data? I mean, extract something like mean X or average path length as a function rapidity based on the data.
Yeah, we can do that. We have this asymmetrical dependent HPT measurements, right, where we can evaluate this this tilt of the bulk. And we have some measurements at BS2 energies, but I don't know if we have measurements at 200 GeV gold or isobar. But I think we can look at this in the data. So this will give you the freeze out tilt distribution. Basically, yeah, the tilt of this QGP bulk at freeze out, which should be directly related to this mean X.
Okay. Okay. And another question, could you turn to page 20? Hello?
Right, 20?
Hello? Uh-oh.
I can hear you.
Can you hear me? Yeah.
I can hear you, yes.
Do you want, can you explain to me why the slope, I mean, the heavier quark has a larger slope than the light hadrons?
So first of all, the error bars are very large for the D0 measurement. So you can see in this plot here, right? If you look at the slope, the error bars are still quite large. So yeah, within uncertainties, I don't know if we can say that it is much larger, but these are also different kinematics, right? For D0, we are looking at very low PT D0 where the collision energy loss and all these drag, drag effects dominate. But here, these are high PT jets, so it's probably different energy loss mechanism and probably different interactions. But with high statistics measurement, this would be interesting to look at to this how the V1 varies, V1 differs for the heavy flavor jets versus the light flavor jets at similar kinematics.
So based on this measurement, we still cannot get a conclusion about the mass dependence.
Right now, no, because our error bars are large and also our kinematics are quite different.
Okay, thank you.
Yeah, I don't see any other hands up. Just maybe, Xing, please.
Sooraj, a very nice talk. Can you go
Thanks.
to the result, the V1 as function of pseudo rapidity you fit with linear and second order polynomial?
Yeah,
Yeah,
this one, right?
Right. So this second order, but the x-axis is eta, right?
Yes.
And the relation between the you call it mean x. Mean x is kind of an average offset, right?
Yes.
And this is also an average effect. I was wondering, assuming I think your hard particles produced at the center of this fiber at certain eta, so your path length is roughly is this mean x. Basically, what I mean is basically the relation between the experimental measured eta versus the kind of exact path length we are trying to investigate in the QGP, how this relation will complicate the interpretation of this picture?
Yeah, so yeah, I think we need more, model studies to make clear statements, because these are for jets on average created. The mean X that I showed are for that is a path length difference for the jets that are on average created at y equal to 0, right? Or sorry, at x equal to 0, right? But in measurements, we always have the surface bias, and where what you measure could be coming on average from a different distribution of jets, right? So not from the average distribution. So yeah, that probably complicates the things. But yeah, if you need to take that into account, you probably need more a detailed model study to evaluate what the exact path length is. But I think that can be done, right? With the because all the ingredients, the asymmetry is what it is. It's just the bias that you have in the measurements, right?
Okay. Maybe also just a follow-up question. Do we have, or will we have enough data in the 2023 and 2025 run to map out this eta dependence?
We would have like 10 times more data. So that is, you should be able to 10 times more minimum bias data from STAR, and probably as Phoenix even more. So we should be able to map this out with much more precision.
Because I was wondering also, you may also, this is for a fixed jet PT, right? And you
Yes.
want to invest with the PT dependence, where
Yes.
the interplay between the collisional and the radial energy loss, they may change as a function of PT.
Yes. Yeah.
Okay. Nice.
Yeah, I hope we can have good statistics. Yeah, at least up to 15 GeV. But I haven't done any detailed projections. But the statistics improvement would be like 10 times for STAR, and yeah, as Phoenix should be much better.
Okay. Juan, please.
Yeah. So thanks. Yeah, very interesting talk. So I
Thanks.
try to clarify. I mean, you see, normally when we try to using, say, V2 elliptical flow, so my picture will be that, the jet really going around the transverse direction. So I know when I say path length, I say what distance going to flow. So in the V1 versus eta, I mean, when you talk about path length, you are mostly dominated by the longitudinal length you discuss, or it's also the transverse? Because it's if it's transverse presence, I mean, the reason I'm having that kind of difficulty to visualize it is somehow, if it's a longitudinal path length, then certainly maybe even some of the colder parton energy loss.
Yes.
I mean, parton energy loss in the colder media or something could also have some small effect on those things. That's one area. Then also I also wonder about because now I tend to think the hadronization, even for jet or something, maybe really kind of through recombination kind of picture. If that's the case, then whether the media has some contribution to what you measured as jet particles in the small cone, I mean, whether it has some effect there or something that you be able to subtract it, reliably or not. I mean, it's anyway, it's just I understand that my question was not clear maybe, but it's just I'm a little bit puzzled myself. So little bit difficult to formulate exactly. I was puzzled about, but I just wonder about how to visualize this physical picture clearly.
Yeah, I think I understand your question regarding whether it is a transverse path length difference or not, right? So from the picture I presented here, we are looking at the path length difference in the transverse plane. So for example, if you look at this calculation from their paper, so this is for a given eta. So you're looking at the profiles of the soft particle production and the hard particle production. So soft particle production is offset along the impact parameter direction, which is the x direction, right? So this is the transverse plane. So the soft particle production is offset, and the hard particle production is not. So if you look at a given eta, so this is in the eta x plane, the right plot. So if you look at a given eta, then what you will see is you have more path length to traverse along along the impact parameter direction one way versus the other way, right? So so on average, your jets are produced at x equal to 0. That means this way you have more path length. This way you have less path length. And since we are looking at still sufficient limit rapidity here, I think we are still limited by the QGP energy, because if you look at centrality dependence, for example, what we see is a response that is reflecting the participant asymmetry, not the spectator or anything, right? So so it's I think we are in the rapidity region that we are looking at, and at these high energy collisions, we are still looking at the QGP energy loss from this path length asymmetry at a given eta. Does that answer your question?
Yeah. So I guess also the question that you showed about the what you call soft particle have the asymmetry, and the hard scattering does not have the asymmetry. So, but
Yes.
right, the issue is at least for many of the jet we are looking at, maybe it really a scattering of two partons, and the two partons x1, x2 is not quite symmetric in the sense that you have a somewhat larger x when hits the target parton, which is a smaller x2, which I just how to visualize when you say the harder component is symmetric, because your x1 parton coming in, that could be that x when it got to follow some kind of nucleon distribution,
right,
somewhat.
Yeah.
Then the x2, if the x2 is more soft than x1, that even follow the soft particle more. So this x1, x2, you hit together. Why it turn into?
But this you have here, you have on both sides, right? So if you look at the cartoon here, so
but it's on both sides. That's okay. But when you go to one eta, right, your eta is not symmetric, because you see the difference there, right? Because the positive eta and the negative eta, you select the different x1, x2 combinations.
But still we are looking at binary collisions, right? So
the binary collision follows the nucleon distribution somewhat. Like if the softer part, I assume like it got to close to the nucleon distributions, then the harder part is the parton within the nucleon, and somehow needs to, it won't be the same magnitude, but somehow that needs to have some kind of
but I think because you have this asymmetry in, like, at negative x, it's it's less dense here and more dense here, so the probability of collisions is It's a probability of collision, right? It's driven by these densities, but then you have the opposite effect at the other x, right? So
Yeah,
so
I mean,
if you look at the number
opposite
of
effect,
binary
that's
numbers,
why your x1, it has a negative slope, right? Positive it has one direction.
but this affects the probability of collisions, right? But if you look at now the number of collisions, I don't think there will be asymmetry along the x direction, right? And I think that
the probability gives you the yield. So when you measure the yield, you get the difference.
So this is what we see in also these simulations also, that the hard profile is not tilted. It's symmetric along the x direction.
Yeah, that's the part. Okay, I would check that paper.
Yeah.
Okay. Well, thank you.
Yeah, thank you.
Okay, thanks. I don't know if there are other questions. Okay, I guess not. So Sooraj, as you know, is still stationed at LBL. So if anyone here want to have a talk to him, he's on the second floor in building 70. So anytime. Yeah, thanks, Sooraj, for the nice talk and discussion. So
thank you all. Thank you for the discussion.
Bye.
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 Thank you.
Bye. Thank you.